All right, let's use the skills and knowledge we've gained so far in this chapter to introduce statistical inference. And also, for this part of the chapter, we're going to assume that we don't know. We are no longer omniscient. We're more like the student pollsters. We're working in an environment of uncertainty. We have a sample mean of 59 and we have a standard error of 2.5, and that's all we are working with. Now, the only unrealistic element that remains is that we derive the standard error with knowledge of the population standard deviation. Later, we will strip away that bit of omniscience as well. Well, here we go. The student pollsters do not know the population mean. Okay, we don't either. But they do have a sample mean, X bar, or sample mean of 59, a standard error of 2.5. Now, what do they do? You know, they're no longer working from knowing that the population means 58. So they use their sample mean as an estimate of the population mean, and then figure out what the probability is that the true population mean lies within their estimate. Using the central limit theorem, the student pollsters know that there's a 95% probability that the true population mean mu lies between their mean minus 1.96 standard errors, 2.5, and plus 1.96 standard errors. Or, to turn those into numbers, 59 minus 1.96 times 2.5, which is equal to 54.1 at the low end, and 59 plus 1.96 times 2.5, or 63.9 at the high end. This is the bandwidth of probability, of confidence. They're 95% confident that the true population mean lies within that interval. The 95% confidence interval, sometimes just called the 95% CI. The 95% confidence interval, or 95% CI, defines the boundaries of plausible hypothetical claims and implausible hypothetical claims. So now we have an inferential tool, and it's blunt, but it's fail-safe, foolproof. Here's the rule. All hypothetical values of mu that fall within the 95% CI are considered plausible. Even though they might just be skirting on the borders of implausibility, we accept them anyway. All hypothetical values of mu that fall within the 95% CI are considered plausible and are not rejected. All hypothetical values of mu that fall outside the 95% CI are considered implausible and are rejected. Let's apply that to a hypothetical. Suppose a skeptic approaches these student pollsters, and let's say the skeptic is, say, the president of the college Democrats or something, and is skeptical of their sample mean that finds that their estimate of the population mean, which is 59, on this 0 to 100 scale. And this skeptic claims that the true value of mu is equal to 66. All right, so what do we do with that claim? Because 66 lies above the upper confidence boundary, which we're going up to 63.9, and we're not going to let our plausible estimates go above that. Because 66 lies above the upper confidence boundary, we know that the probability is less than 0.025 that the true mean is 66. So we don't know the exact probability. We're going to look that up in a minute. But this instrument, the 95% CI, allows us to accept or reject claims based on the 95% confidence boundaries. So we reject the claim. We tell the skeptic that, well, the probability that you're right about it being 66 is less than 0.025, which is very slim, so we're going to reject the claim. Now, a more precise method is to use the normal distribution probability table, which I will demonstrate the use of here. How does this work? Determine the probability of obtaining the observed sample mean, X bar is 59, under the assumption that the hypothetical claim is correct. Now, this is a kind of inferential, sort of counterfactual inferential thinking you have to get in the mindset of when you start testing hypotheses, which we're going to be doing in Chapter 7. So we'll assume that the hypothetical claim is correct, and then find out, under the assumption that it's correct, what's the probability that we would get what we're observing, that is a sample mean of 59, if the skeptic is correct. And here's the formula for doing that. We calculate Z. We have to convert the difference between 66 and 59, which is 7 units of measure. We have to convert that into units of standard error. That's how we can apply the normal distribution. And here's the formula. The conversion is Z equals the hypothetical mean, 66, minus the observed sample mean, 59, divided by the standard error, which is 2.5. Then we'll know how many standard errors the two numbers are apart. So 66 minus 59 divided by 2.5, which is 7 divided by 2.5, which is a Z value of 2.8. Under the assumption that 66 is a true population mean, how often would we get an observed sample mean, a perfectly fine random sample of 100 of 59? The precise probability, the answer is to be found in the normal probability distribution table, which is table 6-3 in the text. And I'll just get out of PowerPoint here and we'll go and look at that table. Here's the distribution of probabilities. Proportions of the normal curve above the absolute value of Z. So only 1/2 of the curve is represented here because the curve is perfectly symmetrical. If we had negative values of Z, we would still look up these values of Z because these are absolute values or magnitudes. Here's how it works. Let's look up a few values that we're already familiar with. Notice that here's the first digit and first decimal of Z. If we got a Z score of 0, we know that half the curve lies above, half the probabilities lie above 0, and half lie below. And sure enough, 0.5000, that tells us that half of the curve, 50% of the curve lies above a Z equal to 0. Let's go down and find the iconic value of 1.96, which we often round up to 2. But let's look up 1.96. Here's 1.9, a first digit, first decimal. Let's go over here, 0.025. 0.0250. Just as we already knew, 0.025 of the curve, or 2.5% of the curve, lies above a value of 1.96. And by the same token, 2.5% of the probabilities lie below a value of minus 1.96. Well, what did we obtain in the example? 66 minus 59 divided by 2.5 gave us a Z-score of 2.8 right here, 2.80. We read across to the second digit, 0.0026. Again, under the assumption that the true mean is this hypothetical that the skeptic offered, 66, we would obtain a sample mean of 59.0026 of the time, about 26 times out of 10,000 by chance. It could happen, but it would be a really fluke probability. So we would reject the claim because by standard inferential rules, first of all claims outside the 95% CI are rejected, and now we can see just how low the probability is that we would have obtained a fluky sample if indeed the true value of the population mean is 66. This is sometimes called the p-value approach. I mean, there are two basic approaches to inference testing, hypothesis testing. One is the 95% CI, which is gained a lot of usage and popularity, regained a lot of usage and popularity in recent times, or the p-value approach, which gives you a precise probability. What did we just do? We locate the calculated value of Z in a normal distribution probability table, which is table 6-3. For Z equal to 2.8, the probability, the p-value is 0.0026. Here's our interpretation. If the population mean is at least 66, we would obtain a sample mean of 59 about 26 times out of 10,000 by chance. Reject the claim.